Okay, well, we're going to do some thinking about mantle plumes now from a isotope geochemistry perspective. And I think one thing this geochemistry does for us here is to connect the deep and shallow Earth. Kind of makes those of us worried about the deep Earth somewhat more relevant, I think. All right, so outline for the talk. First, I'm going to talk just briefly about a few fundamentals of review of few fundamentals of trace element radiogenic isotopic geochemistry. I'll talk a little bit about initializing the system, the fact that we have some debate actually about the nature of the Earth's composition and how it formed, and this leads to some uncertainty. I won't go into that in too great a detail. We'll talk about mantle radiogenic isotope systematics, chemical evolution of the mantle, and we'll conclude the dominant process is crustal recycling. We'll look at the noble gas perspective, which tells us there's some kind of primitive component down there as well. And then this business of Anacanavada, which Barbara mentioned in her opening remarks. And finally, top to bottom and back again, how mantle plumes complete the cycle. Okay, so differentiation of the Earth. Based on what we know from meteorites, the Earth's core formed very early. We know this because asteroidal bodies differentiated cores very early. And metal that probably occurred in the planetary embryos that accreted to form the Earth rather than the Earth itself. Now, an early protocrust might have formed as well as a result of crystallization of magma ocean. But there's no remnant of that early protocrust. Instead, the crust that we have, in particular the permanent continental crust, has evolved over geologic time, and that's occurred through melting of the mantle and transport of that melt to the surface to form crust. What the rate is, how that's changed with time, is somewhat debatable. Partitioning of elements between the crust and mantle. And so this is the big differentiation of the Earth that's occurred over geologic time, is crust and mantle. And that depends on what we'll call an element's compatibility. And that can be related to partition coefficients. Geochemists like to define a partition coefficient between phases alpha and beta simply as the concentration ratio at equilibrium of an element I between those two phases. Conventionally, where one phase is a liquid, the convention is to put the solid in the numerator and the liquid in the denominator. And metal silicate partition coefficients relevant to core formation would be defined in the same way. Now, trace element partitioning, at least particularly for silicates, the kind we'll be talking about, depends mainly on how easily an element can substitute for a major component, because the trace elements don't form their own phases. They have to find a place in existing crystals, and that depends mainly on the ionic charge and the ionic size of the substituting ion. Yes. I won't go into that, but there's a very good model by Bernie Wood and John Blundy that is widely used. And speaking of geophysics, it's based on the Young's modulus, how expandable the crystal lattice is and how easy it is to fit a misfit element into a site. But of course, that has to be calibrated based on experiments. But yes, we can do this theoretically. Okay, so definition, we define incompatible elements as those with solid-liquid partition coefficients much less than 1. Compatible elements are those with solid-liquid partition coefficients equal to or greater than 1. And this refers to partitioning in the way geochemists typically use this, partitioning between silicate melts and phases to common mantle rocks, in other words, peridotite. And because it's that phase assemblage that dictates whether trace elements are concentrated into melts when the mantle melts and ultimately into the crust. Okay, and I'm going to talk a little bit about rare earths to illustrate this point. These elements at the bottom of the periodic table, I've somehow misspelled lanthanides. The thing about the lanthanides is, for the most part, they all have the same ionic charge of +3, with some exceptions sometimes. But let's consider them as always having +3, or most of the time. As we go from lanthanum to lutetium, the size of the ion contracts. So it's very simple. Their partitioning basically depends on ionic size, and here's a plot of that. Here's the ionic radius. There's no promethium in the Earth. And here is the clinopyroxene liquid partition coefficient. And you can see how the two relate. Okay, we often use rare earth diagrams. I'm going to use diagrams like this a little bit, in which the relative abundances relative typically to chondritic meteorites. The relative abundance relative to chondritic meteorites is plotted versus basically atomic number. Rare earths, I'll get to this in a minute, are refractory elements, so their relative abundances in the Earth are the same as in primitive meteorites, to a first approximation anyway. So why do we use relative abundances? Because if we didn't, the plot would look like this. Okay, we have this sawtooth pattern and the decay here. This is related to nuclear stability and the ways in which the elements were produced. By normalizing to chondrites, we can eliminate that. And we can see here that because lanthanum is a large ion, it tends to partition into melts and ultimately into the continental crust. At least a hypothetical depleted mantle shows a depletion in the light rare earths because of their large ionic size. And the terms enrichment and depletion refer to incompatible elements. And this is a Orgeus CI1 chondrite. It's a little bit lower here because the rare earths are diluted by carbon and water and other things. But if we plotted almost any meteorite, it would plot as a flat horizontal line on this diagram. Okay, and geochemists like to incorporate other elements into this kind of rare earth diagram. This is called an extended rare earth diagram or a spider diagram. What we do is we order the elements based on what we think their incompatibility is. As you can see, we no longer have smooth plots. This only works so well. We get anomalies. For example, you see the depleted mantle is more depleted in lead than we expect, and the continental crust is more enriched. Continental crust is also relatively depleted in niobium and tantalum. These so-called anomalies, nevertheless, are diagnostic of certain processes, and both these things I've pointed out are probably related to things that happen in subduction zones. Okay, now let's move on to radiogenic isotope geochemistry. The radioactive elements are shown here in the sort of gray, such as rubidium or samarium, and their decay products are shown in red. So you see we have isotope geochemists have a lot of things to work with. I'm not going to talk about all of these things. I won't talk about rhenium, osmium, or platinum, or lanthanum, barium, or lanthanum, cerium decay system. We'll be talking just about a few of these. Okay, but notice in particular that I'm going to pick on this one a lot. Neodymium and samarium are rare earths. Neodymium a little bit lighter, a little bit larger, lighter, lower atomic number, larger ion, so it's more incompatible than is samarium. Simple relationship. Okay, so isotopic evolution. This is our basic equation of radioactive decay. This is the change in the amount of samarium-147 as a function of time is going to be the negative of decay constant, which defines the rate of decay, and that's a parameter that's independent of everything, basically. times the amount of number of atoms we have of samarium-147. We can, from that equation, derive this one, which tells us that the 143-144 neodymium ratio at the present time is a function of the initial ratio at some initial time, the parent-daughter ratio times this. The key thing, this is the time elapsed since that initial time, and here's the decay constant. Point is, we see that this ratio is going to be a function of just four things. One is the time elapsed since the initial time. This is the present samarium-neodymium ratio that we can measure in the laboratory. Of course, we measure this in the laboratory as well. The other thing we have to know is the initial 143, 144 to know the evolution. And that's where uncertainty about initializing the system comes in. Decay constant for most of the systems are quite well known. It is for samarium-neodymium. Not much debate about that. Okay, bottom line, radiogenic isotopes are time-integrated measures of elemental ratios such as rubidium, strontium, samarium, neodymium, uranium, lead, lutetium, hafnium, rhenium, osmium. And these ratios change as a result of processes occurring in the Earth, and the ratios are sensitive to different processes. Okay, just a review of some notation, and some of the notations I'm going to use here. We'll see mu in just a minute. This is a deviation in parts per million from a terrestrial standard. Epsilon notation are deviations in parts per 10,000 from chondritic value. This basically Chur means chondritic here. And then Annette already introduced the delta notation, for example, for oxygen versus our sample versus some standard. Okay, so what's the composition of the Earth? We'd like to know that, for example, if we're going to evolve neodymium. Where did we start? Okay, so generally we start with meteorites, which we can divide into two classes. Differentiated meteorites, such as these. These are parts of differentiated planetesimals, like this eucrite, which is a piece of Vesta, okay, or an iron meteorite, an asteroidal core. On the other hand, chondrites are collections of nebular dust, okay, and they can be divided into a number of different classes. The main classes listed here: carbonaceous, ordinary, instantite. Chondrites, although somewhat metamorphosed and altered in parent bodies, are samples of the solar nebula from which the solar system formed. Okay, and among the chondritic classes, compositions vary mainly in oxidation state, the ratio of metal to silicate, and in particular, the ratio of volatile to refractory materials. So Murchison is a carbonaceous chondrite, carbonaceous because it's rich in carbon and other things that are volatile, that condense at relatively low temperatures. Okay, now there's good reason to understand why that would be important, why volatility would be important. This is a plot, I think, from Alan Boss about predicted temperatures as a function of radial distance in the solar nebula. The protoplanetary disk and up around the orbit of Earth, we see we're reaching quite high temperatures, enough to evaporate even the most refractory things. As we move outward, so basically at some point almost everything's in the gas, and then the nebula begins to cool, and things condense out of the gas. Jupiter out here, out beyond what we call the snow line, where water ice condenses or even never evaporates, while the inner solar system is still hot. Okay, so the canonical model of terrestrial planet formation is basically this: rocky planets and planetary embryos form quickly in the solar system, in the inner solar system while it's still hot, maybe within a few million years at most of the beginning of the solar system. And they quickly differentiate, as I've mentioned before, within a few million years into metal cores and silicate mantles. In the meantime, the inner solar system becomes cleared of gas and before it's cooled entirely, and so these growing planetary embryos fail to capture their full component of these volatile elements. It takes much longer, perhaps on the order of 100 million years, before these planetary embryos finally grow into full-size Earth-sized planets. On the other hand, again, the Jupiter and Saturn and the outer planets form quickly because they're outside the snow line, because water condenses, we have water ice, and that makes things a lot more sticky. You can build planets much more rapidly out there. And because they form before the gas is blown out, they get almost their full component of nebular gas. So the implication of this model is the main difference between terrestrial and nebular composition is going to be mainly volatility. Here's a plot of the 50% condensation temperatures of elements from a low pressure. That's like 10 to the minus 4 torr, something like that. Very low pressures, temperatures at which they'd condense at. The highly refractory elements. Here's the rare earths, strontium. So all of these things condense at temperatures above the major elements, the things that compose most of the Earth: iron, silicon, magnesium, nickel. And then there's increasing volatility as we go down here. One of the points here is that when we look at chondrites, everything that condenses above this major group tend to be present in chondrites in basically constant ratios, and so we often use this as a reference to model the composition of the Earth. Okay, and I say here these the other thing we can divide, of course, elements into is lithophile elements going into the silicate part, and siderophile, those going into the metal core. Okay, for the refractory lithophiles, we'd expect the silicate Earth to have similar ratios or relative abundances to the chondrites, because they're not fractionated in chondrites. They shouldn't have been fractionated in the Earth. And models of Earth composition rely to varying degrees on that assumption that the Earth too has chondritic relative abundances of those refractory lithophile elements. Of course, rhenium and osmium aren't lithophile, but and also we assume that the isotopic evolution starts with chondritic initial isotope ratios. Now, there's what's developed over the last decade or two is there's some problems. The first is that it turns out when we look at fine enough scale in terms of precision, the solar system turns out to be isotopically heterogeneous. These are two isotopes of neodymium. In particular, neodymium-142 was produced in part by the decay of the short-lived nuclide 146 samarium. So there's another samarium-neodymium pair, but the samarium-146 has a half-life of only 100 million years, so it's really gone very quickly. The point here is that the deviation, now this is mu, so this is deviation in parts per million from a terrestrial standard, of these two isotopes is correlated. And this can be explained by incomplete mixing of nucleosynthetic products from red giants and nucleosynthetic products from supernovae. The heavy elements are synthesized in red giants and in supernova. In red giants by the so-called S process, in supernova by the so-called R process. And so what this is telling us is that these components were added to the solar system, solar nebula, and never completely mixed. So there's some debate about exactly where the Earth should be. Second problem, our solar system is really odd, as it turns out. When we start looking at other solar systems, ours is quite strange. We have a quite empty inner solar system. This diagram shows the plots of extraterrestrial planets as a function of astronomical AU, or distance from the sun. And so here's the orbit of Mercury. And you can see how many extraterrestrial planets have been found inside the orbit of Mercury. Here's the orbit of Earth, Venus, Mars. Okay, so other solar systems tend to be heavily populated in the inner part of their solar systems. Yeah.
How much of that effect, though, is just going to be an observational bias?
Oh, okay,
I mean, 'cause we're
sure.
kind of looking for
but
things not like us, right?
We're not sure. There's going to be plenty of planets outside because the more distant planets are more difficult to detect. Sure. We're not saying that I'm not arguing that the other solar systems just have planets in the inner. The point is, other solar systems have planets inside the orbit of Mercury, typically, in many cases, several. In many cases, they're big, super Earth-sized planets, where our solar system is empty inside of Mercury.
Is this
Okay.
normalized for the size of the sun or mass of the sun?
What's it?
Is this normalized to the mass of the sun?
No. The size on this diagram, the size of the dot is the size of the planet. Now, I mean, it turns out that most of the extraterrestrial planets have been detected around relatively smaller stars than the sun for a couple of reasons. First of all, most stars are smaller than the sun anyway. Second, it's easier to detect planets around a small star than it is around a big star. But this would include stars that are basically the size of the sun as well. So it's not clear that the size of the star is necessarily relevant here. Okay, so the question is why. This led astrophysicists to rethink this whole business of how solar systems form, and in giant planets as well. Okay, and the result has been this grand Tack model. In the grand Tack model, Jupiter forms fairly early, as in the canonical model, but although here it's at 4 AU instead of 5, it forms a little inside of where it is today. But then it tends to move inward. And the other thing to notice, this is all these little circles here are the planetesimals that have formed, or the planetary embryos that have formed inside Jupiter. Okay, so so we're still the same as in the old model, where we form planetesimals and planetary embryos quickly. Planetary embryo meaning something maybe moon-sized, maybe bigger. And Jupiter moves in, and what it does is disrupt everything. The other color code is basically the red or basically dry, mainly metal and silicate. The blue are more volatile rich. This does mix some volatile rich stuff into the inner solar system, helps explain why, maybe where the Earth got its water. But eventually what happens is Saturn moves in as well, and they get locked into 3 to 2 resonance, and then they move back out. But in the meantime, they've thrown, the vertical axis is eccentricity, so they've thrown all these planetary embryos into crossing orbits. And basically, it's catastrophic. They destroy each other, okay? As in this paper in PNAS 2015, the resulting collisional cascade generated a planetesimal disk that, evolving under gas drag, would have driven any pre-existing short-period planets into the sun. And in that scenario, the solar system's terrestrial planets formed from gas-starved and mass-depleted debris that remained after the primary period of dynamical evolution. And the other thing to mention here is the grand Tack model is, why it's given a lot of faith is because it does a really good job of predicting, in the end, the terrestrial planets, their size and position, and the asteroid belt, which other models have always had trouble doing. Okay, so that's just an artist's sketch of what this might have looked like with nothing but debris in the inner solar system. Okay, so in this model, as that stated, the terrestrial planets are then built from this residual debris. I like to think of this as a Roman concrete model of terrestrial planet formation, because the planets are built from recycled constructional debris, just as the Romans built their concrete walls out of, basically the aggregate was pretty much anything they could find. Today we make concrete, we use gravel for aggregate, but the Romans, just throw it in. Concrete is cement, sand, and aggregate. They invented the formula, but they didn't use gravel if they didn't have it. Okay, so what does this mean about the composition of the Earth? It's not obvious that we're necessarily going to be so simply related to chondrites. And these kind of debris disks have been found around other stars. There's a Hubble Space Telescope image of one of these debris disks, and here's the artist's conception. So this kind of thing does seem to happen. All right, takeaway. Terrestrial planet compositions may not be simply related to raw nebular materials, and this introduces some uncertainty in the models since we don't know how to initialize them. Although the differences are probably not going to be large, but they could be important. Okay, now let's talk about mantle isotope systematics. Even in
Bill?
the 1960s, beginning with people like Gast and...
Quick question. In the previous slide? Yeah, there's... No, you had text in the previous slide. Yeah, so that first statement, terrestrial planet composition may not be simply related to raw nebular materials. So basically you're saying that if you plot the composition of any of the terrestrial planets versus the composition of the sun, you wouldn't necessarily expect to see a one-to-one relationship.
Well, of course, we wouldn't necessarily anyway, because this volatility is still an issue. But
excluding the volatile elements, yeah.
Okay, what I'm saying is that collisional erosion is alive and well, right? I mean, we don't, who knows which parts of these planetary embryos ended up spiraling into the sun, and who knows which parts survived. I mean, when we compare the Earth to chondrites, there's too much iron, okay? I mean, there's a big core, okay? One reason might be that silicate parts of these planetary embryos spiraled into the planets somehow because they're strong. The iron parts, because they're stronger, don't break up as easy, survive more readily. And of course, there's Mercury, whose core is 80% of the radius of the planet. So that kind of thing. And in particular, what I mean is the samarium-neodymium ratio of the Earth does not necessarily have to be chondritic. Okay, so even in the 1960s, people began to realize that oceanic island basalts had different isotopic composition from mid-ocean ridge basalts. We didn't even call them, they were called abyssal basalts back then. Okay, and therefore that the mantle was heterogeneous. Even back then, you could see that it wasn't heterogeneous in a simple way. The isotope ratios didn't relate to, there were only two, lead and strontium back then. But anyway, okay, so we knew that these oceanic islands were somehow different. The mantle source was somehow different from the source of mid-ocean ridge basalts. So in a simple way, if we take two of these isotope ratios, samarium-neodymium system represented by epsilon neodymium and strontium 87 and 86, plot them against each other. Mid-ocean ridge plot up here, depleted in incompatible elements, or that's the strontium and neodymium isotope ratios tell us they come from a source depleted in incompatible elements. And here's continental crust, in some sense the complement enriched in incompatible elements, and then the oceanic island basalts somehow in between. In detail, it's more complex, but we can also simplify it a bit. This is a lot of variability in here, but we can break things down into sort of a taxonomy. This is the Baskin-Robbins 33 flavors version of Mantle Geochemistry. I like that ice cream analogy because I'm going to come back to it in a minute. Towards the end of the talk. All right, so, and many of you probably heard about these confusing terms. So the DMM, this is more depleted, more mantle There's this high mu in gold here, EM1, EM2. You might think this is a little bit arbitrary. Also, I think there's probably another component here that was identified basically in a Hart and others paper in '86 called the low ND array. I haven't really shown it here, but so it's not simply, crust mantle. That's the point. And I've color-coded these somewhat, so EM2s are in some version of red, and EM1s are some version of green, etc. And then there's this region in the middle, which Zindler and Hart named prima for prevalent mantle. If we go to another isotope system, we also see the geometry's changed here, but nevertheless, the groups are somewhat consistent. The other thing to point out here is that, we won't go into it, but we don't necessarily know the lead isotopic composition of the Earth, but if we know the Earth's age, we know it has to plot on what we call a geochront. So if the Earth is as old as the solar system, the bulk silicate Earth has to plot here. Actually, I should say the bulk Earth. But if core formation forms early, then the bulk silicate Earth should also be here. If the Earth is 100 million years younger, it has to plot here. And we generally, so mid-ocean ridge, we generally think of these as if let's go back to this diagram. This is bulk silicate Earth should be in here somewhere, this general region. Oceanic island basalts on this, so bulk silicate Earth, well, if we believe the Earth is chondritic, would be there, maybe it would be more up here. Anyway, oceanic island basalts are more similar to what we think primitive mantle bulk silicate Earth is in strontium neodymium space. We look at the lead isotope ratios, they're displaced from any plausible, they have higher, the direction's the opposite. They move away from any kind of bulk silicate Earth. And this is part of what we sometimes call the lead paradox. If OIB are more primitive, why are they more displaced from primordial lead than mid-ocean ridge, ridge basalts, which are down here? Anyway, the other point is that we can still see things separate out into these groups this way. Now this is lead versus strontium. This is prima is in here somewhere. EM1. So geometry changes, but still these groups tend to be coherent. Okay. Now I'm not going to talk too much about hafnium isotope ratios. This is hafnium-176 produced by decay of lutetium-176. It turns out the systematics are pretty closely related. They're pretty similar to those of neodymium, and we get a overall good correlation, and things don't separate out quite so well. But high mu sort of here is still plotting off the general trend. Prima would be in here somewhere. But I'm going to make a point about lutetium hafnium in a minute. That's why I included this. Okay, now this is a three-dimensional plot. We're now looking at epsilon neodymium, strontium 87, 86, and lead 206, 204. And they've been normalized in the sense that we're looking at deviations from a mean. So it's a three-dimensional plot, and make it rotate so you can see how things really look in 3 dimensions. And what we can see, so this is EM2. In detail, we see that there's not a single trend here. Here's another EM2. But there's distinct trends. And here's EM1. Here's our high mu groups, different colors, different islands. But one thing we see is that all of these trend back towards the center. Okay, and what you don't see is, say, any mixing between EM2, any evidence of mixing between EM2 and high mu. Instead, if there's mixing occurring, it's always just going back to this center point. And I think that's an important point. All right, let's move on. Okay, so each hotspot is to some degree unique. We're not dealing with unique components. That's the point. We're dealing with something a little bit different. In some cases, Hawaii, Galapagos, several unique isotopic trends can be identified, but they still fall, but they're nevertheless similar. Despite that, hotspots can be divided into a limited number of compositional groups. Al Hoffman called these species at one point. I think a much better analogy is genera, each of which has several species, the individual island chains. And the point is, the species of each genera have evolved in similar ways. That's why they group like that. Again, they tend to converge on a central point, which is, I'm using Zindler and Hart's original term here, although they weren't thinking about the convergence issue, but they're prevalent mantle idea. Subsequently, various people have rediscovered this phenomenon and called it FOSO-C FEM. Since this was the first one, I'm going to stick with this prima, but if you've heard these other terms, I think they're synonymous. And other than with prima, rarely morb, there is very little mixing or crossbreeding, if you will, between these isotopic genera. And the big question is, what are the radiogenic isotopes telling us about mantle evolution? Okay, first point is heterogeneity in the mantle that we see in oceanic island basalts and mantle plumes is not something produced in the deep mantle. It's a result of processes occurring in or near the Earth's surface, in the upper mantle or within the crust. So what I plotted here are based on available partition coefficients. I realize these are somewhat dicey for lower mantle melt. So we took a perovskite Pericles melt with a little throw in the calcium ferrite phase and whatever that were primitive mantle or bulk silicate earth. This is what the melt would look like, this blue line. If we had a mid-ocean ridge basalt composition down at and melted that in the deep mantle, this is what its composition would look like. In contrast, the earth, if we take primitive mantle and melt it in the upper mantle, we get a pattern like that. And if we compare just two oceanic island basalts, one from Hawaii and one from Mangaia in the Austral Islands, they look a lot more like upper mantle melts than they do like lower mantle melts, with some exceptions. So there's this lead anomaly. Again, I think that's related to recycling in subduction zones. There's this, the Mangaia is one of the high mu, has a potassium anomaly. It's sort of consistent with its low rubidium, inferred rubidium strontium ratio.
How do you make the distinction between upper mantle melt and lower mantle melt?
Based on, okay, so I used the partition coefficients, which people have determined experimentally. And I didn't write it down here, but I plugged it into the partial melting equation, which is just a manipulation of a mass balance, okay, to predict what the melt composition would look like, or what it would, the enrichment, okay.
Can I follow up on that question?
Yes.
So are you saying that melting is not happening in the lower mantle?
No, I'm not saying melting is not happening. Good question.
But it doesn't leave a signature in the trace.
It's not a signature that we see in, it can't explain, say, the difference between oceanic island basalts and mid-ocean ridge basalts, or it doesn't explain the relationship between oceanic island basalts and any kind of reasonable primitive mantle. Okay, doesn't mean it doesn't happen. In particular, if you melt in the deep mantle and the melt has the same density as the solid, it's not going to move. And you're not going to produce, the thing you have to do to chemically fractionate things is, first of all, to have some sort of chemical reaction, and then you have to displace the reactants, separate them in some way. If you don't separate them, whether you melt it or not is pretty irrelevant, right? Okay, so I'm not saying melting doesn't occur. I'm just saying we don't see the signature of it in these things.
Follow up a little bit more. Right, the vertical axis is a log scale here.
Yes.
So what would you look for to see a signature of both melting in the lower mantle and then differential separation of that melt from the solid?
Well,
would it be strontium?
I would expect if I melted the lower mantle and just were able to analyze the melt, it would fall in this blue thing. Let me give you an example here of why we don't think the lower mantle melt business would work so well. If one thing we see is that samarium, which is here, and hafnium, the ratio of samarium to hafnium in most, and you can see it here, samarium, hafnium, in almost all basalts is pretty constant. Okay? If we were to melt in the deep mantle, we'd expect that ratio to be substantially fractionated. We don't see that. Look, the other thing is, look, if we melted in the deep mantle, here's uranium, here's lead. We'd expect a pretty strong fractionation, even stronger if it were more that we were melting down there. Much stronger than we actually see. We don't see the kinds of fractionations we'd expect from deep mantle melting. That said, of course, as I mentioned at the start, partition coefficients on these, those are difficult experiments. They're still dicey. A lot of questions.
Well, you opened a can of worms.
There is one exception to that where there is a strong or a detectable samarium hafnium fractionation in some Archean terrains, which is interpreted to be a result of magma ocean crystallization, which is sort of analogous to a high pressure fractionation process. So it's not a modern process, but it is a process that did occur.
Oh, okay.
As I look at this plot, I think Michael's point about it being a log scale becomes very, very important. So, for example, if I just look at this and I say, loosely an upper mantle is, let's say, half an order of magnitude or more enriched in these elements relative to the lower mantle, my question is, what is the sensitivity to lower mantle melting? So let's say, hypothetically, you put in 20% of a lower mantle melt, 80% of an upper mantle melt. Is that permitted by this pattern? I suspect on a linear scale it is. Am I wrong?
Could you put a little bit in? I guess that's kind of getting away from my point. I guess you could, but I'm still arguing the signature we see is something created in the upper mantle. Whether you put a little bit in.
Bill, I guess both Quentin and I are asking a question since to sample these, you've melted the upper mantle. So by definition, you've got that.
What?
Quentin and I are both asking the same question differently. That in order to get these measurements, you've melted in the upper mantle. So you've already done the fractionation in the upper mantle. Could you see whether a signature of lower mantle melting, or would it be swamped and diluted? Because you have to always melt the rocks and do this fractionation in the upper mantle to see them.
I don't know. Okay, so if you've already fractionated in the upper mantle, you bring it down to the lower mantle, we fractionate it again. I haven't thought about that. Okay.
Last question is how deep did those partition coefficients go?
Oh, I think I was
mantle.
using. I don't know that I don't think there were any data for post-Perovskite, for example. So this would be, above the post-Perovskite. And I forget exactly. Many of these were done by the Japanese. Well, they were, Ringwood went back, but the Japanese have done a number of these experiments. And I'm not exactly sure what the pressure is, but here's the thing. It depends mainly. One big difference you see here is that these highly charged ions, like thorium and uranium, and also zirconium and hafnium, these are +4. These are +4 as well. They seem to be more readily accommodated in deep mantle phases. They're incompatible in peridotite because they're highly charged, and they're bigger than the sites that normally accommodate, say, a +4 iron. But somehow That's where you see the big difference between these things that are more highly charged. They seem to substitute more readily for major ions in the deep mantle phases. So it's the point being, the difference is mainly dependent on the phases than the pressure. I'm not sure whether they did the experiments at 60 kilobar or 60 GPa or 100 GPa. I think that's probably second order. Anyway. Okay, so now I want to talk a little bit about stable isotope geochemistry. That's going to reinforce the inference that the origin of heterogeneity we see in oceanic island basalts, mantle plumes, if you will, is produced mainly in the upper mantle. Okay, and so as Annette mentioned to you, the fractionation factor, the degree to which you can fractionate stable isotopes, decreases with these, or is related to the inverse square of temperature. Okay, so this means when you get to mantle temperatures, unless you're dealing with fractionation between phases in which the atoms are bonded in very different ways, so metal and silicate would be an example of a very different way. Unless that happens, you don't get very big fractionations. So this is Samoa, and you can see these are strontium isotope ratios, and they correlate quite well with the delta 18 in olivine phenocryst. And this is, notice even here the variation, is 5 per mil or so, 4 or 5 per mil, 0.4 or 5 per mil of oxygen isotopes. But you might recall a diagram that she showed that normally we don't see that much variation in mantle olivines. Okay, and the correlation is telling us really that this is also related to something that's been recycled, because this only changes over long periods of time. This can't be just a magmatic process. And this is the tick marks here are percent sediment. Recycled sediment you'd have to add into, say, a mid-ocean ridge basalt composition or something here, I suppose, to change these two ratios. So they seem to plot right along a mixing line. And easiest way to change at the surface of the Earth, you can fractionate oxygen isotopes between water and silicates, water and carbonates by tens of per mil. Okay. At low temperature. In the mantle, it's very hard to produce significant fractionations.
Bill, just real quick. I worry that we compare apples and oranges. I've made plots like this for a long time.
What's that?
I'm worried that we compare apples and oranges. I've made plots like this for a long time, and I worry that we measure strontium isotopes on the whole rock and oxygen isotopes on olivines and plot them against each other, because the assumption there is that strontium isotopes in the olivines are the same as the strontium isotopes in the whole rock.
You tell me, weren't you a co-author on this paper?
Yeah. We specifically reevaluate this plot. We reviewed it.
That's right, but it's hard to measure strontium isotopes on olivines, as you know. So yes, okay, so there's probably the whole rock here versus the olivines themselves. But the reason they do the olivines is because you worry a lot about secondary alteration in these samples. Samoa is tropical, okay, and you really, once you start to rain on the rocks, you can really quickly change oxygen isotope ratios. So the idea here is to pick out nice, shiny, clean olivines that have not been altered. That's the rationale. Okay, mass-independent sulfur fractionation. So normally mass-dependent fractionation is where the fractionation depends on the mass difference between the two isotopes. So that would be to say that in the case of oxygen, if we had so much oxygen 18-16 fractionation, we'd see about half that amount for 17-16. In the case of sulfur, normally we'd expect to see about twice the fractionation between sulfur 34 and sulfur 32. But what we see in what occurs in, say, photodissociation is the fractionation in sulfur 33-32 ratio is just as great as in 32. And there's some theoretical reason to understand why this would happen. I don't have time to go into it. But it can happen under photodissociation. And if you look at, these are in sulfides and sulfates from the Archean, we see this mass-independent fractionation. This uppercase delta is a measure of that, the degree to which fractionation is independent of mass. And the argument is, okay, before the great oxidation event at 2.3 billion years ago, UV radiation could penetrate all the way through the atmosphere, dissociate sulfur dioxide, and produce these mass-independent fractionations. Once we had oxygen in the atmosphere, we developed an ozone layer, and UV radiation could no longer penetrate and produce that kind of fractionation. And there's a whole lot more measurements since then. I mean, there's nothing in the modern world that shows this, except for things that have, in fact, been in the stratosphere. So this uniquely happens in the atmosphere in the early Earth. And lo and behold, Matt again, with Rita Cabral, found mass-independently fractionated sulfur in sulfide inclusions in olivine from Mangaya, basalt from Mangaya Island in the Australs in the central South Pacific. Okay, so how do you get mass-independent fractionated sulfur into an olivine, into an inclusion in an oceanic island basalt in the central Pacific? The only way is to make it the surface, bring it down into the deep mantle, and bring it back up. Okay. I'm showing all Matt's. Matt was also co-author in this paper. Now this is sulfur isotopes in Samoan samples. Also, here's some from the South Atlantic, but here's these Samoan samples again. And we see this correlation with strontium 87, 86. And they're arguing, in this case, if we were just mixing into a mid-ocean ridge basalt kind of thing, if we're just mixing in the upper crust, we'd expect this to correlate that way. They see this correlation. They argue, based on the nature here, that this has to be sediment. Now, this is we're just looking at the mass-dependent fractionation here. So this is different. This doesn't relate to Archean sulfides. All right. Here's another one. I'm sort of picking and choosing some things. These are sulfur and oxygen, as Annette told you, are conventional stable isotopes that have been measured since the days of Harold Urey in mid-20th century. What's happened in the last 15 years is we're starting to see fractionations in heavier elements. And this is the iron 57, delta 57, that's 57-54 ratio. And notice here now the fractionations are quite small. And these are in periddotites, garnet periddotites, and pyroxenites from Hawaii. And we see some significant variation in the iron isotopic composition, somewhat surprising. When people first started doing iron about 15 years ago, they couldn't see anything in the solid earth. Everything they measured was the same, but precision increased to the point where you now see some variation. What's significant here is it correlates with epsilon hafnium, okay? This is the lutetium hafnium decay product. So this is not something that's magmatically produced recently. The correlation tells us it's something ancient. Now, the authors suggest that somehow there's some different fractionation in iron between clinopyroxene and olivine, and they're arguing for presence of pyroxenites in oceanic island basalt sources. Whether that's the correct interpretation or not, I'm not sure, but nevertheless, again, we see correlation between a stable isotope and a radiogenic one. And that showed this as well. Even more recently, we're starting to see some variation in some. Here's Mangaia again. Remember, Mangaia is one of these high mu islands. And Iceland, and which one is that's Cape Verde. Some of these things suggesting some real fractionation in sulfur isotopes, and the sort of amount of recycled material you might need to explain this. All right, so conclusion. Mantle heterogeneity is a consequence of processes occurring in the crust and upper mantle. Although mantle plumes rise from the deep mantle, rock in them acquired its chemical signatures in the upper mantle. And so this was the idea we had back in 82. All right, so how do we recycle material? Well, three ways. One, as suggested here, through subduction, but there's a couple of other ways in which have not received as much attention as they perhaps deserved. One is subduction erosion, and the other is crustal foundering. First of all, subduction. It was Armstrong who first noted, particularly in the Lesser Antilles, the similarity between lead in the volcanics of the Lesser Antilles, which are these gold points here, and the sediment that was outboard of the arc and potentially being subducted into the arc. And that paper was 1971, and he argued that, in fact, sediment, not just basalt, but sediment could be subducted into the mantle as well, sediment being derived from the continental crust. And somehow that finds its way into the arc magma systems, and it comes back out in the arc magmas. We can see similar things. Here's the Central American sediment. You can see here's the Central American volcanics. Here's Scotia sediment, Scotia volcanics. Each one of these things is different, but they're related to their sediment. Okay, and I can show you lots of arcs, but it would be a mess. You wouldn't see anything. That's the thing. Basically, we basically always see. So it's good evidence that that sediment is indeed recycled, and mass balance calculations tell us that not all the lead that comes out in the arcs that doesn't exhaust the amount of lead that's being subducted. So there's enough left over to produce enriched reservoirs in the mantle. Subduction erosion. So the idea here is that oceanic crust could actually abrade the underlying crust of the overlying plate. Okay, and just a cartoon of how this would work. I don't have to go in. I don't have time to go into all the evidence, which is mostly geological and geophysical, and maybe Brad will talk a little bit more about this this next week. But people who've looked at arcs, do find a lot of evidence that somehow we are in fact abrading upper plates. And this is a way to bring that stuff would then be carried down in this subduction channel. And significantly, whereas sediment subduction, we're just recycling upper continental crust, this is a way to bring lower continental crust into the mantle. Here's a table. This is three different papers 5 or 6, 7 years ago, Stern and Scholl. These are different Sterns, by the way. 3 different estimates of the mass flux of subduction erosion. These are in Armstrong units, and Bob Kay has tried to push that term a cubic kilometer per year. Armstrong units. 1.8, 1.35, 1.7. This compared to the sediment subduction. So maybe not in this case, but in 2 out of 3 of these estimates, suggesting we're actually bringing more crust in the mantle through subduction erosion than sediment subduction. And this one is comparable. Add in crustal foundering. And one thing you get here is that estimates are that we're losing as much continental crust as we're making these days. Okay. So the point being, there's plenty of opportunity to transport crustal material into the mantle. Don't really have time to talk about crustal foundering. The problem is this crustal foundering and subduction from a geochemical point of view, it's difficult to get a handle on because we don't actually know what's being eroded, what's foundering. This is, deep crustal stuff, and it's hard to get a handle on that. So I think geochemists have ignored it. Yeah, Barbara.
I have a naive question. When you kind of erode the continental side, wouldn't you be eroding lithosphere mostly?
On the very edge, eventually, but on the the first, on average, 35 kilometers might be in direct contact with the continents, and then I suppose you could also maybe erode the lithosphere, but then maybe at that point it's too soft. I don't know.
So Bill, a quick comment. So some people in this room are really interested in knowing how much continental crust has gone into the mantle over geologic time. And there are 2 issues. One is our present day estimates for the amount of crustal material going into the mantle have huge uncertainties. And then that's the present day. We have no idea how much went into the mantle back in time. How long has continental subduction operated? How efficient was sediment?
Obviously, since continental crust survives today, these things can't match over time. At some point, continental production must have exceeded losses, right? No, you're absolutely right. We don't know what they are over time. Look at those. The losses vary by a factor of 2, but they didn't include, Stern and Scholl didn't include crustal foundering in their, so that would be, if they took those numbers, that'd be up to 4.3. And I'm not, I have no risk. Those aren't my numbers. I don't know how well known. absolutely. So that's a big question. Absolutely. What is the balance? I guess what I'm saying is that, there's plenty of opportunity. These numbers are unlikely to be 0, would be my point. And these numbers are unlikely to be 0. Okay. Okay. Again, geochemists have a hard time with that because we don't know how to deal with it. We don't know what's being eroded. Okay, now, noble gases are telling us quite a different story about a possibly ancient primitive component. The other thing I should say is that none of the radiogenic isotope evidence or variations I've talked about so far could possibly be primordial, okay? Because of the time element involved, we know that these are things that happened on the scale of billions of years ago, couple. 1, 2, 3, you can pick 1, 2, 3. Some people even say 500 million years. But he couldn't have done it 4.5 billion years ago. We're not looking at primordial heterogeneity in these groups or between MORB and OIB based on what I've shown you so far. Okay. Helium-4, of course, is produced by alpha decay. Helium-3 is primordial and is lost from the Earth. And it's a one-way trip for helium, and you can't recycle it. It's degassed during volcanic eruptions into the atmosphere and then leaves the atmosphere. So it's a tracer of primitive primitive gas at least, and primitive material in particular. One interesting thing is that we see, as Matt sort of mentioned, I borrowed this slide from him anyway, that we tend to have the highest 3-4 ratios, not associated with primordial, at least if we believed a chondritic 1-4-3, 1-4-4, but rather something more depleted, something more intermediate, and this would be prima. And I should emphasize that I don't think prima is a single composition. It's a region of isotope space. Okay, so it's not unique, and that region is somewhere in here. So the highest 3-4 are actually associated with this prima group, and the more you move away from that, the lower the 3-4. Okay, so neon, but so helium's relatively easy to measure because there's a relatively lot of it in at least submarine erupted things, and you don't have to worry much about atmospheric contamination because the atmosphere doesn't have hardly any helium. Neon's a much trickier thing to measure, and basically you could probably assume that everything you analyze in terms of basalts or their inclusions is somewhat contaminated with atmosphere. And what we see is these various islands and mid-ocean ridge basalts and such, all produce arrays like this, pointing back to the atmosphere. So that's largely atmospheric contamination. Somehow the fact you've been collecting the thing and getting into the lab, you've gotten some atmospheric neon in there. And so it's really the highest points that we're interested in. Where do these lines end, and how far can we extrapolate them, that sort of thing. A couple of things going on in neon. First of all is mass-dependent fractionation. So the atmosphere is very depleted in the lightest neon isotope, neon-22, relative to neon B is what we see in chondritic meteorites, and this is solar. And this is thought probably to be due to catastrophic atmospheric loss in the earlier in the Earth's history when we lost neon-20 in preference to neon-22. The other thing is that neon-21 is produced by reactions that are initiated by uranium decay, reactions initiated by alpha particles or by neutrons from fission. And so the longer something's been in the mantle, and even more so in the crust, by the way, but we're not going to worry about that, and the higher the uranium neon concentration in the mantle, basically, get rid of that, the further over, I'm pressing the wrong button, the further over you'd be on this nucleogenic production. So this is something of a measure of the degree to which a reservoir's been degassed, because this would be high uranium neon, lower uranium neon. So we see this variation here in mid-ocean ridge basalts, mostly here, fairly degassed kind of reservoir. We see some Galapagos samples, also with Iceland, almost must have much higher neon, higher neon uranium ratios or lower uranium neon ratios, much less degassed. And they also notice they extrapolate way up here, at least as high as meteoritic. They somehow, that neon somehow avoided, the neon in the Earth's interior avoided the extreme mass fractionation that the atmosphere suffered. That's interesting in and of itself. So this is some sort of primitive neon there, is the point. Okay, now, xenon. Okay, first of all, xenon-136 is produced by plutonium and uranium fission. Xenon-129 is produced by iodine decay. And although this plot doesn't do a good job of separating out the plutonium and uranium component, they can be separated out, and you can demonstrate a component of plutonium fission xenon. And the catch is the plutonium has a half-life of only 82 million years. So that variation must have happened within a few 100 million years of Earth's history. The decay, the half-life of iodine-129 is even shorter, 16 million years. So we're looking at variations here. We're looking at some iodine, in this case, iodine xenon fractionation that happened easily within the first 100 million years of Earth's history, of even solar system history. Okay, again for neon, atmospheric contamination. So everything moving back here. So it's really the highest points that you're mostly interested in. If we look at Iceland, it goes only up to here. If we look at mid-ocean ridge basalts, they're way up to here. So mid-ocean ridge basalts have relatively lot of radiogenic iodine, xenon-129. Means in the early Earth, they had the ratio of iodine to xenon must have been quite high. Well, how do you do that? Well, you do gas, you get rid of the xenon and relative to the iodine. And so this is evidence. These come from reservoirs that gassed very early in Earth's history. Iceland and some of these other oceanic island basalts come from a reservoir substantially less degassed early in Earth's history. So I'm not, this is Sir Joy's work. I'm not going to go into too much more detail. The point is, there's evidence for very, very ancient heterogeneity and material in the mantle. Oh, yeah, so this is early degassing brings us this way. Okay, so how much of a primordial component? That's a good question. Constraints on rare gases abundances in the mantle are weak, not non-existent, but they're weak. And concentrations on basalts, for example, we can measure these isotope ratios, but the concentration ratios are meaningless. And degassing in the early Earth and subsequent volcanism could produce variations in rare gas abundances by many orders of magnitude. So basically, we don't have too much of an idea. I remember, I think it was maybe Wednesday morning or Thursday morning, if you're up at Santa Ynez in the morning, I could have this faint smell of a skunk. And I was wondering, I wonder what the concentration of that skunk, I mean, it was very light. You know, it must have been extremely low because the skunks somehow have evolved something that your nose is quite sensitive to. The point being here is that the amount of rare gas involved in OIB is maybe just a whiff. Okay, we don't need a lot because the other end member is so depleted in rare gas that just a whiff might be what we're seeing. Okay, so what about this prima? Recall that prima is the centroid of these points. It can't, by the way, be primitive mantle because isotopically it doesn't work. Trace element-wise, it doesn't work. But it could contain some fraction of primitive mantle. It could in part be primitive mantle. The other thing, as I mentioned before, it's a region of composition space, not a point, at least in my view, so it's heterogeneous by nature. Again, most hotspots have arrays pointing towards this prima. Prima may be some sort of perhaps a mixture of least modified mantle, least degassed mantle, together perhaps with some recycled components. And since prima, at least broadly defined as I've done it, seems to be a component of most OIB, maybe, you know, that's the ice cream and high mu, EM2, et cetera, is just the flavor. And certainly that flavoring is interesting, and it's certainly telling us about crustal recycling, but it doesn't necessarily have to be the bulk of the stuff here. All right, so Barbara mentioned this business of the blind men and the elephant, and this is a story that's supposed to illustrate this concept of Anakantavada, which basically states that the truth depends on one's point of view, and no single point of view comprises the complete truth. And these views are not wrong, merely incomplete. So our task then is to assemble the various views to produce a more complete picture of the mantle. Of course, that's the whole point of CIDER. So what is the picture? What is this beast that we've been putting our hands on? And I'm going to try to, in the last couple of slides, sum that up. First of all, oceanic island basalts, plumes, and LLSVPs. Oceanic island basalts are erupted from these hotspots, and we now know they're located above these LLSVPs, okay? And so we've known this for some time. More recently, well, of course, this has been, been attempts to image mantle plumes, but maybe we've finally got to the point where everybody agrees that we have. I don't know how controversial this is. But so we can now connect through image mantle plumes the LLSVPs to hotspots, oceanic island volcanism, and clearly then what's coming up in these plumes is this OIB source, these various mantle components I've talked about. So I am particularly favorable to this model of Lee and others that came out 2 years ago of these LLSVPs somehow being big mixing machines. So they start out their models with LLSVPs as containing some primitive material into which, so the blue is the primitive material, the subducted oceanic basalt eventually gets mixed in. After time, this gets to be a real mismatch, and one would expect the primitive amount would decrease with time, and eventually you get things would be mixed in at different times over Earth's history. So maybe these LLSVPs are messy storage vaults for dregs at the bottom of the mantle. They perhaps preserve some ancient near-primitive material, but it's been diluted by oceanic crust, plus or minus continental material. It becomes entrained in them. Isotope systematics would suggest the residence time of material in there might be on the order of 1 billion years or more. These flavors, maybe they're not mixed in, or not much anyway, and maybe somehow there's stuff that just gets entrained that's been stored somewhere else in the mantle and gets kind of entrained here as the plumes rise off this hot mantle. Anyway, here's the real, I think, the most important point we can get from isotope geochemistry, combining it with the geophysics that we've seen. And so regardless of the model we choose, the conclusion we reach is that the shallow and the deep Earth communicate with each other. What goes up comes down and vice versa. And their evolutions are intimately connected. So that's my real conclusion. More questions?
Talk. I have some more clarity about isotope systematics now. But the question is, so we are, again, going back to LLSVPs, and the compelling story I hear is you still need communication with the surface, and that communication has to be after a particular time in Earth's history to accumulate some of those enriched signatures. But the models we have are like, okay, these things have to be super early and sequestered down deep. So that communication with the surface, there's no time for that communication with the surface or recycling to create the signatures you've seen in.
Yeah, but we're okay. So
yeah, like how do you deconvolve? At what time do you need to get the surface deep down into the surface to be isolated for some time and then get it deep down into the deep Earth?
Well, the transit times for the mantle are going to be of things going either up and down or less than 100 million years. They're tens of millions of years to 100 million years, sort of. So once we've made crust, and we can start to recycle it somewhat, and okay, so it doesn't look like we got into making crust in a big way until at least 4 billion years ago, and maybe not a big way until 3 billion years ago or even less. That's true. But so that's a question. once you make crust, once you start to subduct it or erode it, the timescales of getting that stuff down are relatively short, and getting it back up are relatively short again. So, but we don't, what would a mantle plume have looked like at 3.5 billion years ago? I have no idea. I don't know that we have anything that we can necessarily sample and say, oh, that's the mantle plume from.
Well, you already essentially defined a lead time. We need 2 billion years of Earth history to create some crust before we then can recycle it into the LLSVPs, before we then can communicate it back to the surface in present-day ocean island basalt. That seems to be like a very hard constraint.
Well, if we weren't, we had some crust. We had some crust, at least a little bit. None, the only thing we got left is less than a handful of zircons from it. But we got some crust that's 4.4 billion years old. We know there was some crust. The oldest surviving real rock is 4 billion years. Okay. Here's the question. Here's another question. How much is there so little very old? Is it so little Hadean and Eoarchean crust because we didn't make it? Or is it because we recycled it all? And, there's a lot of debate about that. So I just don't know. But here's the thing. I'm looking at all the basalts plotted here are no more than a few million years old. We're looking at the modern Earth and extrapolating back, I don't know. I mean, we know that there have been plumes for hundreds of million years, Siberian traps, but going back much more, this model is kind of steady state, but at the same time would evolve over time. If the Lee et al. Model is right, we'd start out in the very early Earth. Plumes would contain primitive mantle. Okay, but we don't know if there were plumes. We don't know if they had primitive mantle.
Because if not, I have a question. Any students? No? Okay, great.
Just given how significant...
Can't hear you.
Given how significant the degassing process is...
I still can't.
Yeah, is your mic on?
Speak really loud, that would help.
So you mentioned how significant degassing is on Earth.
Well, the only thing I got out of there was degassing.
You mentioned how significant it was.
You mentioned how significant it is.
How significant degassing is.
Yeah. I'm just a little bit confused as to how we have a confident constraint on things like the helium 3-4 ratio if presumably degassing was important for those as well. I mean, shouldn't it be a lot lower than what we measure in things like chondrites?
Shouldn't... It is, what a lot lower? The amount of helium or the ratio?
The ratio that they have compared to what the initial solar abundance was.
Okay. Okay. For helium, the initial ratio, we don't necessarily get good constraints from chondrites. The best, it's a little complicated, but the best estimate of the initial helium isotopic composition of the solar system is the Jovian atmosphere, which I think has a helium, it's 120, I think, right? Yeah. So it's in the scale I was using, it goes up to 40 or 50. Primordial is 120. Okay, so it's a lot lower. Okay, so I mean, it's not that those reservoirs aren't degassed. They're just less degassed. That's an important point. Just less degassed.
I have two questions. One of my questions is you were showing the neon B, and I guess maybe I'm missing something, but how does one preserve neon B signature and then also form the moon through a giant impact? Or would that mass-dependent fractionation of neon, would it have taken place also during the moon-forming event?
That would be one. That would be one hypothesis that you had a catastrophic atmospheric escape and severe fractionation during the moon forming event. And so how do you preserve that in the mantle? Well, apparently you didn't degas, I mean, obviously you didn't gas the mantle entirely during the event, otherwise we wouldn't have any neon. So, I mean, but,
okay.
Yeah, yeah, right.
And then the other question is, why invoke, you showed nicely that a lot of, or almost everything that we see can be explained in terms of upper mantle melting, and that a lot of the signals, the different flavors that are added to the ice cream, are due to recycling of things that are produced at the surface. So why ever bring LLSVPs into this story?
Good question. Because the oceanic island basalts are erupted above these geophysically imaged mantle plumes. Okay, the other thing is, there's reason to think that most of the upper mantle consists of morb sorts kind of stuff. Okay, because as soon as you start to spread, what you erupt is morb sorts, the kind of stuff. So we don't think you can get oceanic island basalts out of the upper mantle, isotopically distinct. Okay, so you see them sitting over the mantle plumes. You infer that it's the mantle plumes that are bringing these distinct compositions to the surface. And that's actually a good point, and I kind of skipped over that, I guess. But yeah, and it's important. Yeah, I mean, generally the idea is that the upper oceanic mantle is the stuff that, when it melts, produces mid-ocean ridge basalts.
So I try to learn more from your statement that you made, where you said what phase you have is probably more important than the pressure effect. It is right that the Katsura and Irifune did experiment on partitioning coefficient at 24 GPa, so that includes bridgemanite. But now the question that I'd like to ask is that in mineral physics, we study the crystal chemistry for iron and aluminum, which is much more abundant than the trace elements that we talked about. But we do find evidence that the way iron substitute into the crystal structure and the way aluminum substitute into the crystal structure in bridgemanite changes as a function of pressure as well. So if you take that into account, then would you change the statement? In other words, is it worthwhile for mineral physicists to revisit that problem and going deeper, a greater pressure, knowing that crystal chemistry changes? Would that influence the trace element chemistry or not?
Okay, well, I would not question the idea that the partition coefficients are pressure dependent, but and this, one reason geochemists like to look at ratios is because they're going to be less sensitive. So are they going to be so pressure dependent that we'd see things that were incompatible at low pressure or incompatible at high pressure, or if we look at a ratio of 2, are they going to change more or less in parallel as pressure changes? And I think as long as you have basically the same crystal lattice structure, they're going to tend to change in parallel. So the absolute values might change, but if we look at a ratio, it's probably not going to change that much.
So I'd like to make.
I could just respond to that slightly, which is that there was a CIDER project 4 years ago that actually tried to look at that very effect with the experimental data that was available at the time, and it resulted in a publication. I think Colin Jackson is the first author on that, but I don't remember the details.
You should look it up.
One common theme that comes up in some of these questions is trying to get Bill to admit or to tell us where these different reservoirs are. And the thing is, the dirty laundry here is that geochemists measure the composition of lavas at the surface, isotope ratios to exquisite precision, to 6 decimal places. And we see high mu in EM1 and EM2 and FOSO, and we know that they're down there. But we don't know where, we don't know their distributions, right? That's the dirty laundry. Now, the seismologists, they see different domains down there, redite and blueite. Well, they don't know what they're made out of, right? So you can see the fundamental problem here to get the seismologists and geochemists talking to each other. This is an important theme, I think, that is developing.
Yeah. I mean, that's really true. I mean, when I hear Michael Mangas talk, and he's dealing with X, Y, and Z directions, and these multidimensional matrices, I kind of get quickly lost because that's not the kind of calculus I do, because I don't deal with X, Y, and Z. In other words, don't deal with position.
Are the LSVPs high mu and EM1 and EM2, and the ULVZs are FOSO? No idea.
Well, we'll say that there is differences on average between the African, the plumes related to Africa and the plumes related to the Pacific one. And you introduced Dupal. I like to think of the African one as the Dupal signature, and the Pacific one as a Sopita signature, which is more typically EM2, whereas Dupal's more typically EM1. So there's some difference between these things. But, I mean, you're not going to get me. You guys have played this game and you're one of the people of trying to geographically things, but that's iffy. You're right. We don't have any positional information here.
And maybe a comment is that kind of the meta question is, to what depth should we push that question of trying to relate particular isotopic signatures to structures in the mantle? At what point that stops being meaningful?
My answer to that is probably pretty quickly.
Yeah, I guess my question was sort of similar. We're talking as if these isotopic reservoirs should
Can I hold that closer? I can't.
That the isotopic reservoirs should be
better.
large domains in the mantle.
But now I missed the early part of the question.
It sounds as if we're talking like these isotopic signatures should relate to large domains rather than just really mixed in things that the seismic tomography might not really be picking.
Well, I guess what I'm suggesting is it's the prima that's the mixed in. That's actually the flavor of the LLSVP, and that the other stuff is elsewhere and gets entrained. Okay, so I mean that's what I was trying to suggest.
Okay, I think we're ready to go to lunch and think about all these questions over the weekend. You have something to say?
Just a quick thing, sorry. I guess if you guys, given the board has the topics we came up with, the questions, feel free to brainstorm new ones. If you think that there are too many things about LLSVPs, you should feel completely encouraged to come up with other ideas, talk amongst yourselves, and then on Tuesday, make sure you tell us about them.
Right, so we are having lunch together, and then you're free until Tuesday morning, 9 a.m. We start again. Okay?
Oh, I'm gonna.
And the building will be locked. So if you don't have a pass, you need to find someone that has a pass.